Chapter 6.5 is about partial fractions, and we'll say what that means in just a minute. We might ask, why should we care about partial fractions? Well, you might have seen rational functions in a previous class, like college algebra or something, which is a polynomial over another polynomial. Here's a particular rational function. I'll tell you why I picked that one in particular in just a sec. So rational functions are often useful for approximating other functions, especially if there's horizontal asymptotes going on. So if I have e to the negative x squared, that's this kind of bell curve thing, and that is basically the classical bell curve in statistics. If I define the antiderivative of it, or the cumulative area so far this way, throw in a 1 over root 2 pi, 2 over root pi, that's a function called the error function, which is abbreviated as ERF, which is kind of fun. And it turns out there's no nice formula for that antiderivative, so we have to use approximations. And there's something called a Padé approximation. I think that's how you pronounce it. And that is saying let's approximate something like this with a rational polynomial. And in fact, this polynomial is a good approximation of ERF, at least for like x in the range -2 to 2. After that, it doesn't get so good, but you could make this more complicated and it would be a better approximation even farther out. So we also like rational functions and partial fractions because they help us solve some differential equations. So you might have heard of exponential growth for populations, but a more interesting model is where it grows exponentially for a while, but then levels out at some carrying capacity. And we can use rational functions and partial fractions to solve that differential equation. Partial fractions are also useful for Laplace transforms in engineering and control theory, which is really differential equations. That's what's going on. And in probability and in pure math, we do something called generating functions, which are very similar to Laplace transforms, but people hardly ever talk about it. And rational functions and partial fractions are also useful there. So let's go remind ourselves of a fairly basic integral and then see what we can do with that. So let's do, what's the integral of 1 over x dx? You probably remember that. That is log of absolute value of x, right? Let's do a slightly more interesting one. How about integral of 1 over ax plus b dx? See if you can remember or figure out for yourself what that would be. It's going to be basically log, right? But there's a little wrinkle to it. So you could say it's log ax plus b, but if you took the derivative of that, you'd have a chain rule term with a times a, so we need a 1 over a out here to cancel the a when you take the derivative. We also call that a kind of big 4 shortcut for integrals. So based on those facts, if I asked you what's the integral of 1 over 2x plus 3 plus 1 over 5x plus 7 dx, you could do that integral in a fairly straightforward way using that rule, right? So go ahead and do that and then come back. All right, so we could say it's the integral of the first part, 2x plus 3 dx, plus the integral of the second part, right? 5x plus 7 dx, which would be, just apply this rule. So you get 1 over 2 log 2x plus 3 plus 1 over 5 log 5x plus 7. So the point here is that if I have a sum of fractions that are like 1 over this plus 1 over that, and it's just a linear term in the bottom, it's really easy to take the antiderivative. So the wrinkle comes in next. Let's kind of separate what's going on here. If it looked like this, it would be too easy to take the derivative, the antiderivative of. What if it was not that, but the sum of those two? So what if I did 1 over 2x plus 3 plus 1 over 5x plus 7? I'm not doing an integral here, I'm just doing fraction arithmetic. How would I add those? I would have to find a common denominator. And here, I don't need to think of common denominators like, well, 24 is divisible by 4 and 3 and 8 and stuff like that, because we don't know what x is, so we can't be thinking of factoring like that. We just have to say, well, these two things are their own numbers, whatever x is, and so the common denominator would just be the multiplication of those two things. So I would have to add them by saying, we'll start with the first one and multiply by the second thing. So that way the denominator of that fraction will be 2x plus 3 times 5x plus 7, plus the second thing here, 1 over 5x plus 7 times 2x plus 3 over 2x plus 3. So now the bottom would be 2x plus 3, 5x plus 7. It would be that for this side and that for that side, and since they have a common denominator, now you can add them. And the numerator would be 1 times 5x plus 7 plus 1 times 2x plus 3. And then if you simplified the top, let's leave the bottom as it is for now. You'd have a 5x plus a 2x, so you'd have a 7x. You'd have a 7 plus 3, so you'd have a 10 over 2x plus 3, 5x plus 7. And then if you did multiply out the bottom, you'd have 7x plus 10 over 10x squared plus 29x plus 21. Phew, aren't you glad I did that for you and not you doing it? So now here's the question. What's the integral of 7x plus 10 over 10x squared plus 29x plus 21 dx? If you saw that originally, you'd say, who knows? U substitution isn't going to be very friendly, probably won't work. How could we ever figure this out? Well, if we happened to know that this fraction was equal to the sum of those fractions, then the integration would be really easy. So the whole trick in this section is turning a big ugly rational function like that into the sum of fairly simple rational functions, so we can use this shortcut to take the antiderivative. So just to write that down, this would be the same as the integral of 1 over 2x plus 3 plus 1 over 5x plus 7 dx, which is equal to what we had up there. So the method of partial fractions is breaking this into that sum, and that's what we'll talk about in the next video.